sir, to our participants. Professor Rudra Ghatak received his PhD in engineering from Jadavpur University, and then he started his career from Seri Pilani in fabrication and testing of S-band magnetrons. Thereafter, he served at the National Institute of Science and Technology, Berhampur, Odisha, and at the University of Burdwan. He is presently a professor in Electronics and Communication Engineering Department of the National Institute of Technology, Durgapur. He is the recipient of Ursi Young Scientist Award in 2005. He received support under DST Young Scientist Scheme for the development of UWB antennas for imaging radars. He has more than 250 publications in various international and national journals, conferences, with 1,266 citations. His research interest lies in the areas of fractal antenna, metamaterials, application of evolutionary algorithms to electromagnetic optimization problem, RFID, computational electromagnetic, and microwave passive circuit design. He is a reviewer of IEEE, IIT, Elsevier, John Wiley, and Peirce journals. He has organized a workshop in capacity of workshop chair convener on microwave circuits and antenna, and has been a member of technical program committee membership of numerous IEEE conferences in the Asia Pacific region. With this very brief introduction, I would like to invite sir to take the session.
I thank Dr. Kundu for the nice introduction, and good afternoon to all. Before I begin my discussions, I'd just like to share the group's work, which is under the Microwave and Antenna Research Group, where all my group members and research colleagues have been working in some of the domains of antennas and microwave. So they are contributing in the couplers, the filters, in reconfigurable circuits, and multiband and the broadband sub-wavelength structures inspired from the metamaterial geometries. And they're also working on the DRS in the substrate integrated waveguides and the frequency ranges, and particularly components for the ultra-wideband systems. Now, when we talk about the circuits and systems, obviously antenna is part of the system, and antenna is also should be considered as a circuit. Now, this thought was accepted long ago in the 1930s, but it took a long duration to get well received by various communities. And there has been also controversies on the deliberations given by well-known persons in this domain over the years. Now, considering this fact, I therefore thought to include the topic of presentation somewhere like the antenna characteristics, or I thought that whether I should be specific about its electrically small antenna characteristics, or somewhere the other which can be a little bit different from, because the workshop goes by some modern applications and some innovative antenna designs. And when I thought about the kind of topic I should discuss, I generally took away the certain insights given by persons whose textbooks are quite well known to us so far as the antenna and the microwave engineering community is concerned. One such person's one article published in the IEEE Transactions in 1985 by John D. Krause was a very overwhelming words were presented. And in fact, the year which coincides with this publication was actually celebrating the 100 years of Hertz's antenna, and whom we considered as the first microwave engineer. In that domain, if you look to the words, with mankind's activities expanding into space, the need for antennas will grow. Obviously, if we look in this present decade, you will see that there is a voluminous increase in the domain of the antenna, where a lot of people are contributing to different antenna designs. And the future of antennas, obviously, he predicted that it will reach to stars, and it is a reality. 100 years from now, that means from 1985, the present technology would be as primitive as this transmitter of Hertz now appears to us, because he invented the dipole, the loop antennas. In a sense, if we now discuss about the development some 30 years before, it's still, we think that it is quite primitive for us, but the underlying theories, the underlying insights rather help us to innovate in the way we desire to satisfy the specifications required for present day applications. There I'd like to remind all of you about the views of Jack Ramsay. Perhaps most of you might have gone through this article, Highlights of Antenna History, which was published in the IEEE Antenna and Propagation Society newsletter, which now is known as the AP magazine. Jack Ramsay presented a sentence in the last page of his article. In antennas, spectral expansions always lead to innovations. In fact, in his article, if you look in detail, the dictionary meaning of innovation was mentioned there. Nowadays, we don't need to, there is no need to mention the dictionary meaning of innovation. But it was a hard-said reality that whenever we expanded our outreach so far as the frequency of operations, the application domains, there came the complexities and the constraints. And we adopted to them. Now, I thought that how should we adopt to that? Should we leave behind the facts and only focus on the output, that whether it is satisfying the spec? And in fact, doing so, you will find that you have at your disposal a large number of electromagnetic simulation softwares. At least 20 years before, there were a countable 2 and 3 maximum. I would not choose to name the companies as such. So if you see the developments in the computational electromagnetics and the available commercial softwares, we have been tied down in using softwares to get a desired result. Perhaps that innovation was not being thought of by Ramsay. And if you see the developments which Krauss and Ramsay, through his article of Highlights of Antenna History, just a quick recap of the antenna developments, you can see that such large masks, these antennas cause sparks because of the high power. Then came the planar domain antennas. There were some marvelous things. I think you have got the news that there was this feed snapped recently and this antenna is damaged. More modern applications where the antennas need to be more compact, reconfigurable for various applications, not only for handheld systems, but for transportation systems also. In fact, there is endless application domains where antennas have explored themselves to get different kind of outputs. It has not been only contributing to communication, but in certain areas where we will touch down to one part where this, if you consider an electromagnetic sensor, then it's after all, it's an antenna, but it may not be a good design so far as communication is concerned. but it can be used for sensing. After all, a sensor, the efficiency is not a matter, but for an actuator, the efficiency matters. So when we look into the antenna domain, I prefer to prepare the groundwork in this way, that we start with understanding the simple fact that whenever there are acceleration and deceleration of charges, there will be radiation. Either it will be receiving energy from the surrounding space, or it will be radiating energy or giving energy to the surrounding space. How efficiently it does is based on how effectively the radiator is designed. So the fundamental radiation equation you find in almost all books, textbooks of antenna. You can just revisit and go through the fact that the changing current with time, it produces a changing field. So that changing magnetic field can in turn produce a changing electric field. So the principle is how to make a design such that the currents, they change, they vary. Acceleration of charges or deceleration of charges do occur. Therefore, you might have thought that there are so many designs where you have to cut sleeves, you have to cut slots, then you change the current direction, you alter the current path to actually effectively bring this fact into realization. To understand the radiation, it is also important for us to understand that the radiated energy, although it is due to the acceleration of charges, but it is also important that how the near field energy is getting created. If it is effectively the near field energy is again converted into a radiated far field, then how effectively the environment around the antenna should be excellently guiding the radiation principle. So the near field energy, how it builds up, that is also a key to a successful antenna designer. You can revisit this part in the paper of science, electromagnetic energy around Hertzian dipoles. Very fundamental topic, but in 2001 it was revisited. To more precisely tell about this, you find that there is a region which is close to the radiator, close to a disturbance. So there is a source and there is an effect, which is a fields you can realize. So obviously you can find your own way to express the fields. You can invoke the Green's function to prove the nature of the electric fields. Though that details, it is a textbook work, you can go through them. But the fundamental understanding is the buildup of the energy around the antenna system because of the source, and then a gradual transition from that near field energy which is getting developed to the radiated fields. That is of importance so far as understanding how the antenna you are designing, whatever the configurations, whatever the modern design methodologies you are following, the basic principle remains unchanged. So therefore, I would nudge you for these initial thoughts in considering impedance, input impedance, which you have for a dipole, you have, I think, used the induced EMF method to find the self impedance. mutual impedances, the resonance characteristics, and the antenna Q, the quality factor. So that's why the understanding of the theorems associated with these quantities they have assumed that the network is lossless in its most general form. If you invoke, which will do so by invoking Foster's reactance theorem, it is valid for a lossless passive network. So in the realm of the antenna, which is a lossy circuit, how can we invoke those theorems, those theoretical findings in analyzing these characteristics such that we can at first be sure that the antenna is matched to the network, feed network. The antenna, the power is transmitted to the antenna. The resonance characteristics are met. The quality factor gives you the bandwidth improvement factor and the bandwidth which is required. And the parameters which you find here is pertinent not only when you make a resonant antenna systems, but for designs which are electrically very small. That means you take a geometry, either you look into this viewpoint that you have made an antenna system at 10 gigahertz and you want to see the effects at a much lower frequency. For that wavelength, what is the interaction of that frequency with this antenna system? Because that will be, for that low frequency, it will be many wavelengths small. So the concepts can be compared not only with the gigahertz frequency with the megahertz, but also at the terahertz with the megahertz, with the terahertz with the gigahertz. So you can have these problems satisfied at different frequency domains, provided you can formulate and analyze the impedance characteristics, the resonance characteristics, and obviously you determine the quality factor. So when you characterize them, it's better to separate the two different domains as the circuit parameters and the field parameters. Though in the first instance, we require to know about the circuit parameters to ensure that whether it follows the spec so far as its frequency requirement is concerned. And then you look forward the impedance bandwidth, its efficiency. And once you're satisfied with this, then you see whether how it is radiating at different frequencies, whether there is a stability in these pattern characteristics. What is the beam width if you're designing a particular antenna systems, whether that beam width is required for that application in which that antenna system has to be used up. And if it is a CP radiation, then obviously we need to look for the axial ratio bandwidth. Keeping in viewpoint that not only the antennas are radiating the TM spherical modes or the T's, it's dual T spherical modes, but T and TM both. In such situations, you need to be precisely understanding the current profile. Therefore, I wanted to put the discussions as revisiting the antenna characteristics. And the term antenna, it includes not only those also used for communication circuits, communication transceivers, but it can be used for sensing applications too. To understand the characteristics, we should look into the foundations laid by the persons who contributed to look to the antenna as a circuit element. We have to begin with the distributed circuit theory introduced by Sir William Thomson, better known as Lord Kelvin, and the introduction of impedance concept, very well known as the driving point impedance. Still, if you look to some papers, it may mention, some old papers, if you go through them, it mentions it as driving point impedance. That's the input impedance. So the concept of impedance in AC circuits by Oliver Heaviside, and the dependence of impedance on frequency was expressed way back in 1930 by Sheltonov. And to complete the applicability of these theorems, we have to invoke Foster's reactance theorem, which was inspired by the work of George Campbell. Ronald Foster brought in the Foster reactance theorem, which you have, all of us, they generally go through the network analysis and synthesis domain. We try to find the reactance and the suscitance slope, whether it is positive. If, then what happens? And extrapolation of the reactance theorem for a resonator was by Maclean in 1945. So this is what is the background of the theoretical insights that have provided and ushered our path to more rigorous analysis from the circuit viewpoint, and also we can do so by calculating the energy stored in the electric and the magnetic fields, that is from the field viewpoints. And in that case, you need to invoke the 1964 work of Collin and Rothschild, where the near field and the far field discussions were provided. The energy stored in the electric field and the magnetic fields, WE and WM, were computed from the fields expressions. We can do so very well with the circuit analogy. Now this connectivity, that whether we can achieve our understanding or analyzing and characterizing this antenna as a circuit, I think the two well-known relations, they provide a very nice insight. That in one hand we can find the circuit quantities, and the other we can see the field quantities. And in fact, in many cases, we can obtain one from the other. Inspired by this, we can determine and invoke the distributed circuit theory to calculate the input impedance and use it to find the impedance where the antenna is getting fed. And after getting that information, you can formulate the equivalent circuit either for this transmitting mode or for the receiving mode. And once you do that, you can calculate that what was the power which is radiated, what was the power which is lost. I hope if you have gone through the induced EMF method, you have known how to find out the radiation resistance of a dipole and the reactance part, which evaluates to be 30 sine integral pi. So that's J42.5. So we can easily determine from here that what should be the current which is flowing in that. If you can take the information here, I'm not going into the details of the calculation, just as an example that if you know the radiation resistance, you can know what wire was used to, what metal was used to make that dipole. You can find the loss resistance, and together, once you know, you can find the antenna impedance. And from there, you can find what is the current which is flowing. And precisely, you can determine what is the power which is lost and how much power it is radiated. You can repeat so for any antenna systems to precisely understand its behavior and characterize them. It's an example for a dipole. Whether you go for printed dipoles, you make a slot, you go for any other geometries, you can invoke these principles to calculate the power lost and the radiated power. At this point, yes, anyone has queries? I heard somebody speaking.
No, sir. Probably someone has unmuted, so now it is okay, sir. Yeah.
That's fine. So, when we are discussing about the input impedance, obviously, from your well-known transmission and theory, you generally go for finding the reflection coefficients, standing wave ratios. So there again, you should be precisely understanding that when you are plotting to find the resonance characteristics, you are generally invoking the calculations based on S parameters. For antenna 1%, one needs to be very relaxed because S11, which is the for a one-port network, this S11 is same as the reflection coefficient. Maybe in two-port network, you need to be more cautious in determining the S1. The reflection at port 1 is same as the reflection coefficient. But there is a warning from this paper that the S11 dB that you generally plot, we generally tend to write their return loss, but loss cannot be negative. Negative loss means gain. And if you analyze the variation of these parameters with frequency, it not only gives you the impedance bandwidth, it also gives you some insight that how sharp is the resonance. Whether it is precisely over a single frequency or it is accommodating other frequencies. How much power is getting transferred from the feeding network to the individual modes which are getting supported by the antenna system. Whether that is equal or nearly equal, or one mode is having more power is transmitted to one particular mode, the other mode is not getting enough power, so therefore there's a apprehension that the gain may not be same for the two bands. And if you are trying to merge a large number of such modes, then the constraint is really a tough one to settle down into different modes and allowing all the modes to have a similar kind of a power sharing that is getting fed to the antenna. It generally doesn't happen. But we strike a balance between them. That's the experience of an antenna designer. And that is evolved from your understanding of the current profile, understanding of the vicinity circuits, understanding of the topological complexities of the design, and you have to also look forward towards the matching circuit, towards the feeding network design, particularly for wideband antenna systems. Because if you have a too wide a bandwidth, impedance bandwidth, at the lowest frequency, if you start your design, then obviously a large number of wavelengths corresponding to a higher frequency, maybe at the upper bandage, will be accommodated in the on the antenna system, on this antenna geometrical shape. So what will happen? Because of more number of wavelengths getting accommodated there, there will be a large number of maxima minima in the current profile for a high frequency where the wavelength is small and you have designed it at the lowest frequency. So it's possible that because of this large number of maxima minima, the radiation pattern will have a large undulation. But that will not be, you will have a very idealistic pattern for the lowest frequency. If you are designing a monopole, then you will have a monopole kind of a pattern. But you will see that it doesn't remain a monopole kind of a pattern at a very high frequency, though the bandwidth requirement is met, the impedance bandwidth requirement is met. The same principles or same innate thoughts have to be invoked for any range of frequencies you design. Therefore, I generally don't mention that, okay, this is the property for this range of frequencies, this is the range for frequencies. You have to visualize the current, and in fact, that's a very win-win situation for us, that you can, with a click of a button, you can see the current profile once you model that in any of the commercial softwares. That's the difference, that earlier we had to imagine that current profile. That imagination should be brought back to innovate. Don't always rely on the commercial software outputs just to get the insight on the current profile. Try to imagine that. Just invoking the basic theoretical findings that you have already gone through in your undergraduate and postgraduate courses. I hope it is not difficult for you to invoke those theoretical insights. Considering this fact, we relook at the small current element, which we all prefer to call it as a Hudson diode. If we consider the same dimension for a modern antenna system, we call it an electrically small antenna. And if we think of different strategies of implementing that, either through any means, through any material, not only a metallic antenna, but through any material, we can even extend the frequency bands to newer regime of frequencies, perhaps in the terahertz domain. So if you look into this, we can explore and formulate the magnetic vector potential because of the current and get the field. And once you compute the field, some interesting facts get revealed. You will find the variation has 1 by r term, 1 by r square and 1 by r cube, which are well-known facts that there are electrostatic variations. There are some which is induced fields, and there are terms which govern the far field. Therefore, if you are told to find what is the radiated energy and what is the reactive energy stored, obviously your calculation should not involve, when you are only determining the reactive energy stored, you should neglect those field contributions which are in the far field. You should restrict them in your analysis in the near field domain only. Then you can precisely measure that. And when you want to measure only the far field, then obviously it is a direct consequence of the fact that the other terms become very negligible. But if you are precisely measuring the fields near to the antenna system, near to the current distribution, near to the current disturbance, there you should be precisely considering the fact that we should not include those contributions which are not within the reactive field domain. Obviously, you know what the different regions around these radiating systems. So in doing so, when we want to find the energy stored in the reactive field, that is the region which is so highlighted by a circular shape around the antenna system. If it is a dipole or a monopole, you would expect a TM01 spherical mode. If it is a TM01 spherical mode, the near field is predominantly electric energy is stored. And if it is a T01 spherical mode in a loop, then the reactive energy which is near in the vicinity is predominantly magnetic energy which is stored. And when you calculate the quality factor, from the fundamental definition from calculating the fields, 2 omega WE by P rad, 2 omega WM by P rad, you have to consider that WM, that is for the magnetic energy and the other one is for the electric energy. So precisely, you will find here that if it is a TM01 spherical mode, then the reactive fields are mainly electric energy. And for TE, the reactive field is magnetic energy. Considering this fact, we have to proceed to find the quality factors from the fundamental definition. Obviously, these definitions are well known in textbooks. You can go through Peter A. Rizzi books And you know the relationship because we included all the circuit terminologies here. It's fine. Energy stored in the resonant circuit by power lost in the resonant circuit. Obviously, the energy stored in the resonant circuit, which in this case may be an antenna, and the power lost, radiated power. But in doing so, it's the maximum of the electric energy or the magnetic energy which is stored. So therefore, we have to include that 2 omega WE or WM by P rank, which 2 factor tacitly incorporates the fact that is either the maximum of the electric energy or the magnetic energy. It's not for the general cases like WE plus WM. That's the difference which you have to put in your calculation. Because for a dipole, the reactive energy in the vicinity of the dipole is predominantly magnetic energy. And the bandwidth calculation, perhaps you go find the resonant frequency by 3 dB bandwidth, then you generally find the quality factor. This relation is true only when we have a very sharp resonance. A very narrow band of frequencies which is getting where the resonator, which has been somehow made to radiate. The antenna is also, the topology will be that of a resonator. A square patch resonator can be made to work as a diplexer. It can be made to work as an antenna system also. The same square patch of length lambda by 2. But if you find the single mode of frequency, then fine, this definition will work out. But if there are large number of closely spaced modes, because of the modern applications, you need to go for multiband. And therefore, the complexities, if you improve the frequencies and make a large number of modes for at a millimeter wave frequency, you need to cater to one particular applications where some 23 to 29 gigahertz is required. You put in large number of modes there, then obviously, if you try to find the Q for the lowest resonant frequency and try to apply this, then you cannot calculate the bandwidth. This calculation will not be satisfactory. This is for only those cases where this fundamental resonance is well separated from the higher order modes. In that case, this can be true. In other cases, you have to calculate. So when calculation of the Q, you can be wrong when you include the radiated field as the stored energy. If it does not include the interaction between the radiated and the reactive field components, and for most general case, we can consider here that the stored energy which you generally try to mean is the reactive energy associated with the imaginary part of the Poynting vector, not total field energy. So therefore, in computation from the fields, you have to be precisely understanding this, that whether you are including radiated energy or you're unknowingly you are including the radiating energy, then it's your Q calculation will be erroneous. And for computing the stored energy, you can invoke and find the WEWM. Universal relations are there. You can find you can go through the Collin and Rothschild's work in evaluation of antenna Q. It was presented way back in 1964. Obviously, we can find the input impedance once you calculate the energy stored in the magnetic and the electric field. And you can separate them too. And invoke the fact, once you calculate the reactance and the suscitance part, then you can invoke Foster's reactance theorem. And if the slope is positive, you know very well that it alternately passes, it should give poles and zeros. And the Macklin showed that this particular fact can be extended to arbitrary electromagnetic structures so long as their driving point impedance, mind it, driving point impedance is the input impedance can be established. Till you can establish the input impedance of that resonator, which you are supposedly thinking of making it as an antenna, then you can analyze and find the resonance frequencies and the frequencies for certain resonators where you will get a transmission zero. But is it so direct that you can apply the Foster's reactance theorem and invoke it for the antenna systems separately? Though it gives us some useful insights when you apply it for the transmission line, you can find the resonance and the anti-resonance. What is the frequencies that you can determine? Just calculate the input impedance, input admittance. If you want to calculate the transmission poles, you equate the input admittance to 0. You can solve the equation. You can solve for the transcendental equations, you can get it. If you can determine the transmission zeros, you can equate the input impedance to this, equate it to 0, solve for the transcendental equations, you can get that. But when we go for the antenna systems, first thing that you have to do is separate the matching network. There is a feeding network which may include the matching segment with the antenna equivalent circuit. It can be done for both TM and T spherical modes. I'd like to precisely mention that you can use it not only for small antennas, for resonant antenna systems also you can follow it. So there may be various viewpoints in regarding this. An electrically small antenna where TM spherical modes are there, the reactive energy is precisely electric. For TE modes, the reactive energy is precisely magnetic in nature. Invoking that, you can calculate the total antenna impedance. From the frequency plane, you have to move it to a complex frequency plane. We can define it like that. And once you go to the complex frequency plane, then you formulate the Maxwell's curl equation, take the Laplace transform of the Maxwell's curl equation. Then after you get the impedances, you can invoke Cauchy-Riemann condition to arrive at these two formulations which can give you the direct implication of the Foster's reactance theorem. This is what is the Foster's reactance theorem. And you can calculate the resonance frequencies by invoking either of the Foster canonical forms. That means either we can make a parallel tuned circuit for a electric antennas. You can go for a series RLC for a magnetic antennas. You can invoke the Foster canonical forms to go for the equivalent circuit. Then find the ZD. So for antennas, you can apply Foster's reactance theorem also. We can do it. Though antenna being a lossy network, but Foster reactance theorem being valid only for lossless passive networks, we can invoke them. Proceeding in this way, if you can try out with an equivalent circuit of a probe-fed patch for multiple mode of operation. A large number of tank circuits giving you the equivalence for different modes of frequencies. Calculate the setting, separate the real and the imaginary part, and you can look forward to finding the Q also once you get the input impedance. So you can find the electric energy and the magnetic energy, understanding whether it is a electric antenna or a magnetic antenna. You can insert it on small also. It's either an electric antenna or a magnetic antenna. Find what is the fields, precisely determine the energy stored in the electric field and the magnetic field, whichever is required either for the TM or the TE modes. But when you do so, you have to precisely calculate the reactive field. Don't include the radiated field, radiated energy in that. That will give you a wrong calculation for that. And if you know about the input impedance, which is a well accepted fact that we could determine the input impedance either through the Foster's canonical form of series or parallel resonance circuits, then you can easily find input impedance and then find the reactance with the reactance part by the variation resistance part. XA by RA will give you the antenna Q. So from the antenna input impedance, whatever the calculations, whichever way you do it, because over the years, you have the work of KE by Yaxian and Best and Hansen. But when you do so, just try to find the input impedance at the point where it is fed. It's not considering the matched networks also. You have to exclude the matched network and then determine the input impedance. That's the key to precise calculation. So there has been, as I was initially mentioning, that these observations on the quality factor determination had been over the years. There has been many contributions. There have been many controversies also. Like there are comments on the case result that at certain frequencies the derivative may become of the reactance may become negative. So in that cases, it is not satisfying Foster's network theorem. In that cases, it is very rarely it occurs for the antenna systems, whatever the new developments are also there. So in that case, to avoid that, what was done? They had taken the absolute values and the Yaxian and Best results were put forward. There are further simplifications of Hansen where you can use it to determine the quality factors. Using Gay's result, we can see that for a simple dipole, we can find out a closed form result for the quality factor. Similarly, for the loop, we can find it out. Now you can change the dimensions, whether you go for planar structures, you change the shape of the, invoke new geometrical insights into the shape. That are the innovations you may be doing, but the underlying theoretical insights will remain same. So you have to appropriately follow these strategies to achieve these results. So when we discuss about the quality factor, there has been a lower limit also. That means how maximum bandwidth, size, they're all interconnected. If you make the antenna very small, it's possible that you cannot achieve the desired bandwidth. But how small an antenna, but still satisfying the bandwidth, then what should be the quality factor bound was a topic which got initiated ever since the entire antenna community started thinking antenna as a circuit. In fact, the initiation was in the year of our country's independence in 1947. A paper was published by Harold Wheeler, and he was categorical in introducing certain terms like the radiant sphere. That is, he assumed that the antenna, it's suppose a dipole, is surrounded by a sphere of radius a, which is lambda by 2 pi over 1/3 the wavelength corresponding to the lowest resonant frequency of the antenna. So the concept of radiant sphere was included, and he provided a limit, but that was later on found that it's not so lower limit, but it's a little bit higher. We cannot have that luxury to achieve such a wide bandwidth for a very small antenna. Then Maclean provided this updated expression in 1996. And we can extend it to determine the Q using the, once you can get the VSWR, then you can use the bias formula which was presented in designing wideband microstrip antenna. You can use this VSWR minus 1 by Q into root of VSWR to determine what is the bandwidth. But it's a significant contributions regarding the use of Q in determining the bandwidth. Now, why these equations or the lower limit got revised over the years? The reason is that Chu, when calculated this, did not consider the reactive energy stored within the hypothetical sphere. Hansen and Collin introduced a modified Chu formula, and they came out with this closed form, this kind of 1 by root 2 into Ka plus 3 by 2 into Ka cube. It will find mostly 1 by K cube A cube plus 1 by Ka. So this got a little bit revised. So you can use this to determine the Q. Once you know the radiant sphere, how small you want to make it, what is the compact dimension you have, what is the region in which you want to limit the size of the antenna, because the antenna designers don't have the luxury for certain designs to you have a big structure. So possibly for many wireless transceivers, you end up in getting a very limited space. So once you have to utilize that space to achieve that bandwidth or to provide that requirement, frequency requirement over that domain, I hope you have to calculate through this method to exactly find out. And therefore, the proposition was there, the bandwidth of the antenna can be improved with those geometries which effectively fills the available volume. A direct insight was using fractal geometry. People started using fractal geometry for one such reason, that effective volume was very well filled up by meander lines, by fractals curves and structures which could effectively entirely be confined to that radiant sphere, but was effectively filling that. That's the reason that we could achieve that wide bandwidth using modern initiatives on the antenna geometrical modifications. That's again, you can appreciate that the geometrical modifications have been there in innovations, but the theoretical insights have remained same over the years. So you can follow more details into this choose paper, this Hansen and Collins paper on the choose formula. And once you decide on the bandwidth, you have to invoke Bode-Fano criteria, because the realizable bandwidth is not that which you desired. So you have to keep the redundancy in your design. So if you are planning that if you include from one frequency F1 to F2, you have to start calculating such that it is little bit below F1 and above F2. Then the practical realizations can be done. And for that, the bandwidth improvement factor can be also calculated once you know the deflection characteristics of the topology which you are designing. And these things can be now very well initiated from the numerous electromagnetic simulations that you are easily having access to. Earlier, we had to go for a large number of prototypes, then find it, and then see how much is the improvement. So you can invoke these relations for bandwidth improvement factors. The latest article being in this is that of Hansen's, which is correct impedance matching limitations. It came out in the Antenna Designer's Note in the IEEE magazine in June 2009. So that can be invoked to find what is the realizable bandwidth for the antenna system. So when characterizing that, when we want methodically that you have to analyze you're separating the reactive energy and the radiated energy, it helps us to analyze whether it is an efficient radiator. For that reason, we define the antenna efficiency. It's Harold Arnold Wheeler, whose one of the findings was very complicated theories were made simple for application in industry. That was done. His work spanned way from 1940s. And those initial thoughts, you can see that the radiated power by radiated power plus loss. Now you can easily know that how you can find the power which is lost. So you can find the radiation resistance, the loss resistance, you can calculate it. But to precisely find what is the input impedance, to find the loss, you have to calculate by covering the antenna with either a spherical shape metallic container or a cylindrical of radius equal to the radian length lambda by 2 pi. The radiation resistance part will be eliminated and you can find precisely the loss resistance. For any designs you are doing, suppose you are designing a monopole, you are designing the multi-band, very miniaturized antenna systems. So you can fix it up using a ground plane. You can take a separate copper sheet or a aluminum plate. And nowadays, I think if network analyzers are available almost in all institutes. Earlier, it was not, we had to go for different kind of measurements for determining the input impedance. Now we can use a network analyzer to do so. So therefore, we generally transformed our discussions from using that method precisely in conjunction to a network analyzer. So you can see how for a port 1 measurement, you can find the Z-in, and then with the Wheeler cap, you can also measure the Z-in. So a copper plate or a aluminum plate, that can be, you can drill the central conductor with the feeding cable, you can connect it and put the antenna system. So then maybe the antenna can again be having you can extend the ground plane with the additional copper sheet or the aluminum sheet. And you can use a simple 1 liter paint tin. I've just hidden the company logo for this particular. But you can use a simple tin to cover the antenna system, and it can act as a Wheeler cap. And you can perform the measurements and find the loss resistance. And you can then invoke whatever the equivalent circuit, either the series or the parallel, and then put in the values to find what is the radiation efficiency. The shape of the cap is not critical. Preferably cylindrical caps are more easier to get it. The cap has to make a good electrical contact with the ground plane when working with monopole antennas. It is not necessary to have the cap perfectly centered over the antenna system. The room in which the measurement takes place could cause significant changes in input impedance. So it's better that you avoid other extraneous RF sources or scatterers. Then it's better to have an anechoic environment for this measurement. If you don't have precisely a dedicated anechoic chamber, then you can set up your own observers in a particular region where you can first cover up with aluminum foil to allow no EM radiation. This ambient radiation is nowadays from the mobile radio signals. You can cover it up and then put in the observers, and then you can perform the measurements. Because the frequency ranges in which the lower frequency ranges are not that low that it cannot be possible in most of the labs which we generally work in. And you can find the thickness of the shield, though that satisfies this particular requirement, that you can find the skin depth. So it should be greater than the skin depth. Obviously, those tin sheets container are following this limitation. This limit is achieved by that. Now, before we go for wideband antenna efficiency measurement, I'd like to invoke the certain critical aspects so far as design is concerned. For the wideband antenna system design, because when we judged about the impedance matching, the broadband matching, equivalent networks, multi-mode circuits where the modes can be brought close together, that equivalent networks are done. So we should touch down upon the feeding techniques also, such that we can achieve that broadband. To do so, let us invoke the simple monopole. I hope this is a very common circuit which many of us as antenna designer, they generally try to make it for the achieving a wideband monopole antenna design. This is the antenna system. And they may feed it with the help of a ground plane on the other end. This is the top conductor. Or they may bring another design where it can be ground plane is the same plane, that is a coplanar waveguide design generally they look for. So you can subsequently make a 50 ohm feed line. Either you can invoke the CPW synthesis relations and determine what should be the spacing. There should be this spacing S, this width W, this spacing S for determining that. Again, you can generally, you know that the ground plane, because it is in conjunction to the antenna system, the currents playing on the antenna system, they can be also tuned with the presence of the ground plane, that the current precisely which is getting circulated in this region, they can be influenced by the presence of the conductors in the vicinity. You can look from this viewpoint. But if you want to make a broadband, then you will see that the term bevel is used. Rather, this is not a parametric study that where you change this particular shape, you will find a large number of shapes and sizes. And I wondered that where the modifications of these geometries will really end up with. The important aspect is understanding the fact that we actually are designing an antenna whose input impedance we know, considering the point where you are giving the feed. This is the point where we are giving the feed. Now, once you determine this input impedance, you have to find out that whether the impedance is properly matched over the wide range of frequencies with the feed line. So generally, if people start beveling these edges and make the edges, the corners of these regions are generally our target regions where they are altered and they come up with different antenna shapes. But the principle behind, you can, instead of just changing this shape, if you think of that what is the requirement, you can go for different tapered transmission line profile. The Z you can vary with the length. This shape of the impedance profile can be changed. That impedance profile can be either a tapered profile, it can be a triangular profile, it can be again a tapered transmission line like a Klopfenstein taper. It depends on how you change the parameters to get the different kind of insights so far as the tuning the edges are concerned. It may be an exponential tapering, it may be Klopfenstein taper. So this tapered transmission line concept should be invoked in changing the shape of the, or making this kind of a tapered feeding arrangement such that the antenna geometry gets matched. So this is one kind of tapering. You can have a exponential taper, triangular taper. There can be Klopfenstein taper. And this tapering you can extend to the ground plane edges also, such that the tapered transmission line concept can be in to determine that whether it is getting matched over a wide range of frequencies. You can find the impedance profile, synthesize the reflection, and then you can easily evaluate that whether the bandwidth improvement factor is satisfied, whether how much bandwidth improvement you are getting. So this definitive analysis of the antenna systems rather paves the way for antenna designs which you can have a control upon the design parameters. You need not wonder that how you got the result. So a precise insight, either in the feeding network design, in its analysis part, in characterizing part, you have to go for the design insights. And precisely when you are going for wideband antenna systems, the efficiency for that, the Wheeler cap method also needs some modifications. Such kind of wideband antenna systems, like for those you have seen for the, precisely these kind of designs are for UWB systems. You can extend the designs with different ground plane shapes in different topological formats. And you can extend it to other frequency ranges also. But the antenna efficiency measurement, which was discussed just now, which was for a very narrowband antenna systems, the problem is the reflection caused due to mismatch is ignored in this approach. The reflected power is neglected. For wideband antennas, mismatch reflection losses is the most significant factor which cannot be neglected. Therefore, if your antenna design itself caters to definitive approaches of making a proper impedance matching network that feeds the antenna system, then I hope you can, with that approach, improve the radiation characteristics or radiation efficiency of that antenna itself, rather than putting a lot of efforts in, again, altering the radiator shape to get a better radiation characteristics. Because at some point of time when you go through, you may be getting a wide impedance matching, but if you look into the antenna characteristics, it's very poor gain for the antenna system. That's the reason that those impedance matching networks were not designed to actually allow the current to flow properly, allow it to radiate, didn't allow it to have the proper formation of the energy in the near field region of the antenna. Then only it will get radiated. First, it should build up in the near field of the, in the vicinity of the antenna, energy should build up and then it should get radiated properly. So for doing that, to include the reflection measurements, we try to find S11 in the free space. When the antenna is in free space, then put the Wheeler cap and then you try to measure the S11 with the cap. So the S11F is the reflection coefficient of the antenna in its free space configuration. Then it's the reflection coefficient of the antenna when it's placed in the Wheeler cap. Then the power reflected due to mismatch. Then receipt power is P receipt, REC. Then P in is the power which is input. then power lost in the antenna on transmission, then power lost in the antenna on reception, then power lost in the CAN wall. So gradually we can synthesize them to end up getting the results accumulated only for the with respect to the S11 with the Wheeler cap and S11 in the free space. So we end up with finding P rad by P in, which is efficiency, as from the S parameter measurements. And we can determine the antenna efficiency using these parameters for wideband antenna systems. So a closing note on the, so far as using Wheeler cap in determining the, characterizing the antenna efficiency, Wheeler cap is a close conducting container in size such that it doesn't couple to the near fields of an antenna. So you're confining the energy within the cap. It should be properly grounded. It should be properly placed on the conductor ground plane. For a narrowband, this container may be a sphere or a cylinder whose radius is lambda by 2 pi. You can choose the cap size to be little over lambda by 2 pi at the lowest frequency of the frequency band over which you are measuring. At some frequencies, the cap appears to reflect back. Obviously, the techniques, when they have advantages, so there are errors in measurements also. So these errors may appear from the cap appears to reflect energy back very efficiently. At other frequencies, significant energy is dissipated due to the reverberation within the cap. Multiple reflections within, it will be falling down. That also can happen. So these two may be the sources of error in your measurement, but still it gives a good characterization for the antenna systems. So using this antenna efficiency measurements or characterization, let us just look back to this particular example, though we wanted to explain it because we'll have a hand-on calculation of the antenna efficiency. We took a dipole of length 12, 3 centimeter, diameter 2 millimeter. Obviously, it's a copper wire whose conductivity you know. The operating frequency is 1 gigahertz. The radiation efficiency can be determined. You can calculate it. 97.97%, very nice efficiency. But if the same is now, the frequency is now 100 megahertz, whose wavelength is 300 centimeter, then this acts as an electrically small antenna. And now you can determine the antenna efficiency again. Determine the antenna impedance, and then you can find out for the real and the imaginary part. This efficiency computes to be 60.97%, or at least 37% it has come down. This efficiency is much lower than that which was at the resonant frequency. Normally, electrically small antennas have low efficiencies and high reactances. This high reactance has to be properly taken care of when matching. This is the trick or the underlying factor that when you make very small compact structures, its reactance you see it's 6524.3 units. J minus J, it may be inductive, it may be capacitive. This high reactance has to be taken care of. They are not popular, so we can better to use it for a different application, though it can sense. If you are using it for very short distance communications, okay, it's fine. Very compact structures for certain applications, we don't mind that whether it is a poor radiator or a very good radiator. But a poor radiator can also be good sensor because the efficiency, the electromagnetic field sensors, that their efficiency is not required. It can just detect. Our work is to just get the field detected. Then we can use it. So a sensor which can detect and measure. Obviously, the purpose of sensor is to detect and measure. Efficiency can be 5% also. It's immaterial for us. Linearity of response should be there. Obviously, input and output, what is sensing and how it is reproducing the values. So antenna as an EM sensor can also be, it can be used for receiving or detecting fields in the vicinity. You can either use a loop for sensing the magnetic fields and a simple straight wire, very short straight wire to detect electric fields. Now, what's the main difference between the device used for transmitting and receiving and one which is used for measuring? That's the key difference between the field sensors and that of an antenna. So when it is used for measuring, one term which comes into the characterization is the effective length, where you know the open circuit voltage and the effective length, you can find the electric field. The relation is in front of you. If you know the open circuit voltage, then you can find the electric field. The strength of the electric field, you can know that how much is the electric field strength. So one parameter that generally helps us in doing that is the antenna factor. The receive voltage multiply with the antenna factor, either for the electric or the magnetic, and then you can find the electric field strength or the magnetic field strength. You can express the antenna factors and others. This electric field strength can be in dB, microvolt per meter. That also you can do, express it in log scale also. So when characterizing the antenna systems or the as a field sensors, we can just think of that almost there has been over 100 years, there has been a lot of development so far as the theoretical insights are concerned. There has been a lot of controversies around the insights, but the innovations and developments should take care of the suggestions which are put forward to efficiently calculate the quantities such that our design remains fixed with the specifications we are at hand. I would like to end up with a quote from Wheeler that you should work hard to find the easy way. Thank you.
So thank you very much, sir, for this wonderful and informative session covering all the foundation and basic things of those are very important from an antenna engineer's perspective, the fundamental antenna parameters. And sir, a lot of appreciation messages and questions I could see in the chat box. If you give permission, then I can take few
Obviously,
questions.
yeah, we should have, because
yes,
we generally, I learn a lot from the questions.
Yes, sir. Yes, sir. So, yeah.
But
Okay.
I'm just seeing one by one, but I'm not able to jot down.
Right, sir. So, actually, Jeet asked 3 to 4 questions, but at present he left due to a meeting he mentioned. So, I'm taking the questions so that it could be beneficial for the other participants as well. So, what Jeet asked at the very beginning, that due to which phenomena the guided waves propagating from a time-varying source leaves the metal flared out mouth of the transmission line and are transmitted to free space. Which phenomena or principle is responsible for separation of guided waves from conducting transmission line?
That's the fundamental radiation principle, that the near field energy gets accumulated and then starts flowing. So one of the difference is that when in the circuit, just you can take it from this, let us invoke the Gauss law of electrostatics. So in the circuit, there is it is bound within the conductors where there are charges, in this electrons are flowing through the conductors. So there, you have divergence D is rho v. But in the free space, there is no free charges. In that case, when it gets detached from when it doesn't have any conductor to support, when it doesn't find any transmission line or a medium to support its propagating modes, it gets detached. There, when in the free space, when it gets the interface of the free space there, due to the absence of free charges, divergence D is equal to 0. And therefore, you can see those field lines. The electric field lines also becomes closed curves. You can observe the electric field lines. Those electric field lines are plotted. These electric field lines are also closed curves. So when it is in the radiation field, so that's a magnetic field, changing magnetic field, then an electric field, it's a chain which is created. So this way propagation is occurring.
Yes, sir. Exactly. So I am taking the next question that is asked, that what is the significant factor which contributes to design a multiband antenna with same gain?
Same gain is a different issue, but you have to invoke the first principle, that is when you go for multiband, try to provide enough space for all the modes to have their current supported within the geometry. Then you can expect that whether when the current is not getting stagnated or current is not getting reflected back because of sudden, because for one mode you designed it such that the current can flow. For the other mode, the same structure which helped the first mode, for the other mode it is creating a stagnation, that is a standing wave can be created there, or it may be some divergence in the current profile. So you can have either a slight shifting frequency, or you can have that may not be radiating properly. So there are the differences. So the first way to look at them is to provide suitable current flowing path over the antenna system. Just look very, very clearly with your antenna. Whatever topology you have that, just where you make the feed network, just find out that whether the current is able to flow, whether it has enough space for the current to flow. Whatever the designs you are, so to say, innovating.
Yes. So the third question is that can we define resonance as a state where resonance of a system is maximum or minimum, say voltage or currents? Or how do, means any suggestion or comments from the honorable speaker?
Response of a system, can we define resonance as a state where response of a system is maximum? I think one should go to the book of Ryder, where resonance is properly defined. So there you can take up the chapter on resonance from John Ryder.
Okay, sir. So again,
you can just make a summary of the different. Some comments may be same. At least you cover up one question from different.
Right, so right, different persons, right, participants, right. So Professor Raghavan, Professor Raghavan from NIT Trichy, appreciate your talk a lot because he said because it's a completely different flavor and a different kind of presentation. So he appreciated. Then
he's a very respected teacher.
Right, sir. Right, sir. Right. So yes. So the next question is, sir, that how can we say that reactive energy around dipole is magnetic in nature?
Reactive energy. For loop antenna, it is magnetic. The near field, for the loop antenna, it is magnetic. For the dipole, where it is spherical TM mode is getting transmitted. For spherical TM modes, the near field energy will be largely electric in nature.
Right, sir. And the same participant is also looking for some suggestion about the book on equivalent circuits.
There is no such exactly books for equivalent circuit.
Right.
If you look to the Ronald Foster's paper, there also you will find the canonical forms. Then you have to find out that, I think I mentioned one paper of Gay where Foster's reactance theorem was extended to antennas. Then you can yourself think of that whether you will go for a series electric antenna or magnetic antenna, which way you classify the design you are doing for whatever applications. So it is now these kind of definitions are not only for defense application antennas, for space applications, for in general antenna systems. In fact, you can invoke different laws also to make it frequency independent antennas, where there are large number of modes may be set up because of the principle where you think in modern antenna designs you have invoked the quasi-complementary structures of Mushiake. The complementary, self-complementary antenna systems of Mushiake was invoked. So there also large number of current modes are generally set up in the antenna system. So it depends on what is the input impedance you get, and from there you have to find what is which canonical form will be suitable for the particular equivalent circuit development.
Yes, sir. The next question is it possible to design antenna temperature sensor for temperature measurement?
Used for that. So because the variation of the dielectric parameters with respect to temperature, that property has been used to see the change in the resonance frequency. So the calibration has to be done. So what is the change in the temperature? So what is the change in the dielectric constant? And then what is the change in the frequency? So after calibrating, you can then tell that it can sense this temperature difference. So this frequency change means this amount of frequency change means this is the temperature change was there.
Right, sir. Dr. Mahadevan from ISRO, I believe, he asked that
how will be effective it will be. That's a different question.
Yes.
Whether you can actually overcome the actual temperature sensors for the other, which are generally available in the market, that's a different question.
Right. Dr. Mahadevan asked that isotropy can also considered as a parameter for wide beam or omnidirectional antenna apart from efficiency. Generally, this parameter is not given importance. So he might be looking for your comment on that.
I just can you please show it in the screen, because I'm not able to see that. I'm not able to
yes,
follow
sir. Yeah, V. Mahadevan from ISRO, Dr. Mahadevan, he asked at 3 p.m. and 3:34 p.m. actually.
3:34. Okay, let me come to that time. Yeah, I got it. Isotropy can also considered as a parameter for wide beam omnidirectional antenna apart from efficiency. Generally, this parameter is not given importance. It depends on the kind of applications where it is required, because I said some monopole antennas are printed monopoles have been also devised because we want isotopic radiation from them. Not all antennas with applications require directive radiation pattern. So where there is omnidirectional radiation characteristics are required, where we go for different manifestations of this monopole. That's the reason printed monopoles find large number of applications are there.
Yeah. So again,
excuse me. Can I?
Yeah. Yes.
Yes, sir.
I'm Mahadevan. This isotropy is really required for us to know how close it is to the isotropic antenna for an omnidirectional antenna case. See, wherever, specifically in cases of spacecrafts where we want a very wide beam radiation, or mainly for tracking telemetry and commanding. See, you know it, once the satellite is launched at any location, we want to have the signal. So we look for antennas which are having an omnidirection in nature. So for the designer to know how close are we to an isotropy, this becomes a very important parameter. I think possibly this is so in case of satellite spacecrafts. Similarly, it may be useful for aircraft also. But not much of mention is made about this particular isotropy, which is very important for these applications.
Yes, because the concept of that hypothetical isotropic radiator, based on which we generally the theoretical insights are given,
Yeah.
We generally don't have this kind of an antenna systems which can really radiate equally in all direction. In fact, a dipole also is not purely isotropic.
Correct. No, that's only for a comparison purpose we need to use it. That's it.
Yeah. So
my intention is only to say that such an important one for these applications is not highlighted much. So possibly in the this thing in the coursework which faculties are involved, so they should give an indication of such a parameter also. That was okay. Thank you very much, and it was an excellent lecture to hear. Thank you.
Yeah, thank you, sir. Now, I'll be taking one or two more questions, sir. So the next question is theoretically, Arun Raj asked that at 3:37 p.m. theoretically lambda equal to c by f, but practically antenna size is decreasing, means radiation decreases. Then how small antenna work at high frequency? Then how small antennas are actually working at high frequency? Are you okay? So that is the question.
Yeah, that's a limitation. That's the, you have to find the Q, and that the lower bound will provide you how small can you make the antenna.
Right. So I would like to frame it in a different fashion, sir. What we have experienced whenever we are designing is basically on FR4 substrate, the patch antennas. In case of small antennas, sir, especially the antenna pattern beyond 8 gigahertz, that deteriorates, means compared to the simulated patterns, whatever we are getting from the simulating tools, the measured results are not actually at all similar. Maybe beyond 7 gigahertz, 8 gigahertz after that. So what could be the possible reason for that, sir? Means
there was a little bit break in your. You can just suggest what kind of antenna you were using.
UWB antennas, sir. I'm mentioning ultra wideband antennas.
And you are using FR4 substrate. That I got your.
Yes, sir. And when we are measuring the pattern above 8 gigahertz, especially beyond 8 gigahertz, the patterns are not actually maintaining the similarity with the simulated results. So below 8 gigahertz, it was okay, but above 8 gigahertz, the patterns are actually
not at good, or the simulated results were good.
Yeah, simulated results are good, sir.
Simulated results are not. Many times it happens because with the software, sometimes it happens you don't get a good, exciting result with the software, but you could get very good results in the using while measurement. So therefore, I specifically asked that. Now, the problem may be that when you design, there are certain factors, like I was telling, there are certain elements in your antenna design, ingredients which you call it, which you use to make it multi-mode in nature. First, you have to make it multi-mode to allow different modes to get inside the antenna topology for covering the entire topology.
Right.
So when it was being, so those structures, they were being analyzed from a viewpoint that it took the current profile, maybe not that instance current profile, but it was able to calculate from the near field, it does a Fourier transform and finds the far field. So it was giving you a far field result, but in practical application, your feed, that was when the feed was connected. Now, in other cases, in actual application, the feed which was connected, the SMA connector which was given, that may not have allowed the proper communication of the signals above that frequency towards the antenna system. The feed is ideal when you simulate it. So here, because of your fabrication errors, you may not be able to set up that current, that small, whatever small, because generally a small current also, if it gets set up, then it will allow some radiation. But maybe at that frequencies, the current is not able to flow properly in that.
Yes, sir. So, if even in case of, sir, for a circular disc monopole antenna, patch antenna, maybe for UWB coverage from 3 to 20 gigahertz, suppose, or maybe beyond 20 gigahertz. In case of simulation, also, we could see that if we check the surface current, we are getting a higher order of resonances for 12, 14, 16 gigahertz, maybe. But the patterns at the very same frequency points are not actually correlating. It is getting deteriorated, even at the simulation results. So, is there any relation? Because especially these things happen for very small size antennas, maybe within 3 mm by 3 mm dimension. 30 mm by 30 mm dimension.
30 mm is quite large.
Quite large, sir. Yeah. But even in such cases, beyond 10 or 12 gigahertz, the simulated patterns are also getting deteriorated from the usual figure of 8 or bidirectional patterns.
For monopole, you are telling?
Monopole, sir.
Okay, so you are not getting that uniform. That I was telling that at higher frequencies,
right, sir,
current, the large number of, because the high frequency is small wavelength. So a large number of wavelengths are accommodated inside the antenna. So there are a lot of maximum minima. At certain cases, you will have the far field getting cancelled, and certain there is a destructive interference will occur, and certain constructive interference.
Yes.
So you will have a lot of undulations in the pattern. So it's never ideal. Practically speaking, you will never get uniform radiation characteristics over a very wide band using such monopoles.
Right.
That's the reason
even the ground planes are also.
That's the reason
ground planes are also used to contribute in radiation for such small antennas.
That's the difference. See, there are. You can just see that for the certain cases, for the space programs or for certain defense programs, we generally, maximum cases, we try to resort to the existing age-old antenna systems, like preferring the lens antennas, preferring quadrifilar helix antennas for space programs. So it's we hardly go for such kind of geometries for very wideband systems also.
Yes, sir. So,
in fact, a more uniform pattern is generally given by Vivaldi antenna system. It depends on your application. So, antennas are generally used for the existing programs, for certain programs. But for communication systems and for general exploration, that whether antenna is working fine or not, for there are like buzzwords like 5G, 6G communication, whether it's going to work or not. So that's why any designs can be preferred. But for exact communication applications, for precise applications, you have to look back to the fundamental antenna designs which are truly frequency independent. So those structures are generally followed.
Right, sir. And as you have given very informative insight about the antenna efficiency measurement following the Wheeler-Cap method, sir, one question came in my mind, that at many cases when we are designing the integrated antenna structures like using FSS or ANC, in such cases, which efficiency would be better to measure, the single antenna efficiency or the total efficiency?
Yes, I could not get you. Single antenna and total antenna means?
No, total efficiency, sir, I'm asking, means the efficiency considering
P dat by P dat plus P loss. That's the
right, sir.
Yeah, that's not about total. It's completely different. You have to find out that only. That's antenna efficiency.
Yes, sir. In some of your papers, I have read, sir, that the SMA connectors are also designed during the simulation. So, during the simulation environment. So, could you please give some insight? Because that's very interesting that I found. Is there any?
Because the SMA connectors and the waveguide feeds, which are generally used to instead of the SMA, we generally get a waveguide port feed. But waveguide port feed gives a very theoretical aspect of how the field should be launched for a microstrip or a CPW structure. But that generally is so ideal situation doesn't persist for practical applications, where we generally use a coaxial connector to feed the antenna system. Okay. So by modeling the SMA connector, we try to avoid the discrepancies with the measured result.
Yes, sir. So thank you very much, sir, for this very wonderful and informative session. And I believe there's a lots of takeaway for all of us from this session. So, and thank you, sir, for all your patience and allowing us to answer so many questions. Thank you, sir. Thank you very much.
Okay.